Radioactivity and nuclear energy. To describe how neutrons produced in a fission reaction may be used to initiate further fission reactions, and this is called a chain reaction. We have a large nucleus which is relatively stable. A slow-moving neutron is captured by this nucleus. It then becomes unstable and splits into two roughly equal parts and releases 3 neutrons. So this is as it starts to split. This is 2 separate fission products, and we produce 3 neutrons. These 3 neutrons go on to be captured by other nuclei, and they also will divide, and they will fission into 2 more parts. They in turn will produce another 2 or 3 neutrons, and the process continues. This is a chain reaction. Here the neutron is captured by the uranium-235. It splits into 2 roughly equal nuclei. Actually, this is roughly 2/5, this is 3/5, and it also produces 3 further neutrons. These go on to cause further fission. Then the nuclei that are produced might be different. This is xenon and strontium, this is cesium and rubidium. There's no fast rule to say which is produced, but what is important is the atomic mass is conserved. So we have 235 plus 1 would be 236. Afterwards, we must produce a mass of 236. So this is a chain reaction. Notice that we have 1 fission causing 2, causing 3, it could be 4 or 6 fissions afterwards by all these other neutrons that are produced. The neutrons that are released are moving very quickly and they have a lot of energy. Also, these particles, these nuclei, are moving very quickly with lots of energy, and also radiation can be produced. Right, here we have an example. This is uranium-235. It captures a neutron, then becomes uranium-236, but for a very short time it is very unstable and will almost immediately split into 2 roughly equal sized nuclei and then produce 2 or 3 neutrons. Uranium-236 now, unstable, splits barium and krypton plus 2 neutrons. So observe this again. The neutron is absorbed by the uranium-235. For 1 moment it makes 236, then it's unstable, it splits and produces neutrons too. 236, unstable, splits. It produces a great deal of energy. These 2 particles, these 2 nuclei have a lot of energy, the neutrons have lots of energy, and a gamma ray photon can be emitted. Where does nuclear fission occur? In power stations, in warfare. So you will need to be able to balance nuclear equations. Here, for example, you will be told, this is barium, krypton, you will be told the atomic numbers and the atomic masses. Notice we have 235 plus 1 is 236. These add up to 2, 3, 3, which means we are 3 short of 236, which means there must be 3 neutrons being produced. So we have 1, 2, 3, 4 examples of this. You should try to figure out, in each case, what happens. Try this one, and then try the answer. Try this one. This is 233. The next one is the last one's a bit more difficult. 131 plus 89 is quite a bit shorter of 236. Here we have nuclear fission. We'll try with a very large density. Notice because the nuclei are very compact, very close to each other, that there's a very high likelihood that the neutrons that are produced are going to cause further fission. If these particles are much further apart, it's much more unlikely that this will happen. So we are left with only 2 nuclei that have not fissioned. So we have a very high density, and we're likely to have a continued chain reaction. We'll try with a different value of the density. We'll try with a larger volume. Having a larger volume means there is more space between the nuclei that can fission, which means it's less likely to maintain a chain reaction. There we have 1, 2, 3, 4, 5 left at the end. Brings us up to the idea of critical mass. If there's only a small quantity of the uranium-235, the neutrons that are produced during fission escape from the material, leave the material, and do not get the chance to cause further fission. So if the quantity is very small, then you are not likely to be able to prolong a chain reaction. If there's more than this critical quantity, or the density is higher than a critical value, the neutrons produced are likely to cause further fission, and therefore you can sustain a chain reaction. So you need to understand the concept of critical mass and critical density. So the basic line is each fission must cause at least one more fission for the chain reaction to be sustained. So we have to distinguish between controlled nuclear fission, which is in a power production, and uncontrolled nuclear fission, which is in nuclear weapons. So we know that a neutron induces the fission. We get thermal energy, which can be in terms of the photons or fast-moving particles. In power production, this nuclear reaction is controlled by controls. What they do is that they absorb some of the neutrons, so some of the neutrons are not allowed to cause further fission. But you have just enough neutrons which allows you to keep the rate of energy production at a constant rate without it escalating. Nuclear weapons, however, they do not have control rods, and the reaction is not controlled. All the neutrons which are released during the fission are free to cause further fission, so you get a prolonged chain reaction which escalates. You need to know about fuel enrichment. Now, the nuclear fuel, the uranium-235, is only 0.7% when you purify uranium. And this is not enough to sustain a chain reaction. This is lower than the critical density. The most abundant isotope of uranium is uranium-238. So, when you dig out uranium from the ground, you purify it to get the pure uranium. Most of it is 238, which is not fissionable. And only the tiny part of it, 0.7%, is 235, which is the fissionable isotope. However, there's not enough of it, it's not dense enough, it's not concentrated enough to cause a chain reaction. So you must do what's called fuel enrichment, which means increasing the percentage of uranium-235 to be at least 3%. Then it will have the critical density, then it will sustain a chain reaction.